This is our pre-lab video for our molar mass of a metal lab. The purpose of this lab is to find the molar mass by reacting our metal with some hydrochloric acid, collecting the hydrogen gas that's produced, and then doing some calculations with that amount of hydrogen gas that allows us to calculate the molar mass of the metal. Now, if you recall, metals react with hydrochloric acid. I'm just going to use aluminum as an example here. When they react with hydrochloric acid, it's a single replacement reaction. The aluminum takes the chloride, and because aluminum makes +3 charges, chlorides make -1 charges, and so when we put them together, they would make aluminum chloride, like this. And then the hydrogen is going to be left by itself, but hydrogen is diatomic when it's pure, so we'd always get H2. Now, because we're collecting some hydrogen gas, but we're relating it to our metal, we need to know what ratio our hydrochloric acid and our metal are going to react with each other. And that means we need to be able to put together a balanced chemical reaction for our metal. I'm going to use the example of aluminum. If I were doing this experiment with aluminum and I react it with hydrochloric acid, they react in a single replacement reaction with each other. The aluminum goes with the chloride and the hydrogen is going to go off by itself. When we put aluminum and chlorides together, aluminum makes a +3 charge, chloride makes a -1 charge, so they get together in an AlCl3 type ratio. And then the hydrogen is going to be by itself, but hydrogen is diatomic, so we're always going to write it as an H2 when it's pure hydrogen. So I have my balanced chemical reaction, or I have my chemical reaction, but it's not balanced yet. And so to balance it, it looks like I would need to put more chloride. So I'm going to put a 3 here first, but then when I do that over here, I would only be able to, if I put a 3 here to balance out the hydrogens, that gives me 6 hydrogens. So I think that has to be a 6. So this would react in a 1:6 to 1:3 ratio. Now, knowing what ratio the hydrogen gas and your metal are in will allow you to collect some information. So collect things like pressure, volume, and temperature, calculate moles, and then relate those moles to moles of aluminum. Now again, the purpose of this lab is to find the molar mass of a metal. And molar mass has the units of grams per mole. So we need the grams of the metal per mole of the metal. And to find each one of these parts, the grams and the moles, we're going to use a different procedure. To find the moles of the metal, like we just talked about in our balanced chemical reaction, we're going to find moles of hydrogen gas. To do that, we need to collect volume, temperature, and pressure information about the hydrogen gas. To calculate or to find the grams of metal, we're just going to weigh out a piece of metal that we use for our reaction. Now this portion really isn't that hard. We could just use a scale to do that. So what I want to concentrate on is the procedure and the calculations for this part down here. To find this information about our hydrogen gas, we need to be able to do this reaction, reacting our metal with the hydrochloric acid, in a container where we can trap the hydrogen gas that's produced. We also need to be able to collect the volume, like measure the volume of it and measure the temperature of it, and somehow find the pressure. So to do that, we're going to use a burette that's been inverted. Now at this point, it might be helpful for you to pause and go to the lab setup video so that you can see the actual procedure here. But just to quickly review the burette setup, we have our burette here, and in the top we have a stopper that's holding a piece of metal. So that's the metal that we're going to react. In my example, I used aluminum. So I would take a little piece of aluminum and I would wrap a string or a wire, like a copper wire, around that piece of aluminum, and I would give myself a little tail, and then I would insert that down into the burette, and I would put the stopper in there so that it holds it in place. Now in my burette, I've made sure that the stopcock is absolutely closed, and then I've filled the bottom portion of it with hydrochloric acid. And this hydrochloric acid is pretty dense. It's a really high molarity, and so it's kind of syrupy, and it definitely stays in the bottom of the burette. Then after I put some hydrochloric acid in there, then I filled the rest with water, all the way up past my metal. Now my metal isn't going to react with the water very quickly at all, but if I then take this whole setup and I turn it upside down, the hydrochloric acid is then going to be at the top, and it's going to start to flow down to my metal. So this is what it would look like once I've inverted it. The stopcock would be at the top, and my metal is down here at the bottom. The hydrochloric acid started up here, and it starts to flow down to my metal. And when it hits my metal, it starts the chemical reaction. So if I'm using aluminum, it starts this chemical reaction. Now if you watch the lab setup video, you can see that when the hydrochloric acid hits the metal, it starts to produce hydrogen gas. The hydrogen gas is less dense, so as this reaction is going on down here, the gas starts to flow up to the top and starts collecting in the top of the burette. Now the reason why this burette is down into a beaker is because that stopper, it's a stopper, but it has a hole in it, and that hole is so that the pressure on the inside of the burette that it's in can equilibrate with the pressure on the outside of the room, and that'll allow us to find the pressure of the gas in the burette. And so this beaker down here, this beaker has some water in it, and that water is just so that we can equilibrate the pressures without letting extra gas go into our burette. It's basically, we are setting up something kind of, we talked about it in class, something like a manometer. A manometer allows us to equilibrate two pressures or relate two pressures to each other without letting the gases touch. And that's what we're doing with our little beaker full of water here. It also helps because the stopper does have a hole in it, and hydrochloric acid is falling from the top of our burette to the bottom of our burette. And if there's a hole here, some hydrochloric acid is going to get out, and it's good that we have a beaker around this so that we can collect that hydrochloric acid and not let it just fall onto the counter. All right, when our reaction is done, we will know it's happened because the bubbles have stopped forming, so we aren't getting any more bubbles. And when the reaction is done, we're going to have an area up here of hydrogen gas that we've trapped. The rest down here will be water, and all of our metal will be gone. So all the metal will be reacted. Our job then is to find the pressure, the volume, and the temperature of this hydrogen gas and use PV equals nRT to use those things and to calculate the moles. And again, once we found moles of the H2, we can find moles of our metal, and that'll get us closer to the molar mass. So let's talk about how we can use this setup to find these variables. The first one is the pressure of the hydrogen gas. To find the pressure of the hydrogen gas that we've collected up here in the top of the burette, there's a couple things that we need to think about. First is that we are hoping that it is in equilibrium with our atmospheric pressure. That doesn't always happen exactly because sometimes the water level here is not the same as the water level in the beaker. And if that's true, the pressure of the gas, so the hydrogen gas, or the gas trapped in the burette, is pushing down, and atmospheric pressure is pushing down on this water here. And if they aren't pushing down the same amount, these two water levels aren't going to be the same. Now you might get lucky, and they will be the same, but that doesn't usually happen in lab. So what we do is we measure atmospheric pressure, so we get that from the barometer. And if the water levels are the same, that's the same pressure as the gas inside the burette. But if you look at your setup when the reaction is done, and there is more water in the burette, so if the water level in the burette is higher than the water level of the beaker, it means that the atmospheric pressure that's pushing down on the beaker water and pushing the beaker water up into this, that is higher than the pressure of the gas pushing down on that water column. And that's the situation we see much more commonly. In that case, the pressure of the barometer is higher than the pressure of the gas, and it's equal to the pressure of the gas inside plus the pressure of this water column. So it's the pressure of all this gas plus how much pressure that water is exerting. So one of the corrections we need to make is for this water column if your setup has a difference in water levels here. When you rearrange this equation, you get that the pressure of the gas is equal to the barometric pressure minus the pressure of the water column. And your results section will tell you to do that. Now, if you're taking this lab online, we used a slightly different procedure where we ensured that the water levels were equal to each other, and so we don't have to do this type of correction. So in that case, the pressure of the gas is equal to the barometric pressure. So for the pressure of gas, one of the corrections that we need to do is take into consideration the water level difference if your setup had a water level difference. The other correction that we need to make for the pressure of the gas is that when we collect this gas up here, we're collecting it over water. Remember, collecting something over water means the gas bubbles up through water, and the gas that you trap is not only the gas that you think, so it is hydrogen gas, but it's also a bunch of water vapor. And so anytime we have a wet gas like this, we know that the pressure of the gas is equal to the pressure of the gas we think we're collecting plus the pressure of water. Remember, that's called the vapor pressure of water. And the vapor pressure of water is something that you can look up on a chart. And the pressure on the chart varies with temperature, so we need to know the temperature of the room so that we can look up the vapor pressure of water. And we're trying to find the pressure of our hydrogen gas, so we would take the pressure of the gas minus the vapor pressure of water. So the other correction that we need to do is we need to correct for the fact that we are working with a wet gas, and we find that the pressure of the hydrogen gas we're trying to study is equal to the total pressure of the gas minus the vapor pressure of water. So these are the two corrections that we will need to take into consideration when we're finding the pressure of our hydrogen gas. Your results section will lead you through those calculations, remind you to do them. This one you will need to do only if the water levels are different, but this one everybody will need to do. All right, now let's talk about finding the volume of our hydrogen gas. The nice thing is we're doing this in a burette, and burettes have those nice tick marks on there so we can measure volumes. The issue is that burettes aren't read upside down like this. And if you haven't used a burette in a little while, I'm just going to redraw this over here. And I'm just going to kind of draw the bottom of it. So a burette has a stopcock at the bottom. So kind of like a little twisty thing right there. And remember when you were using burettes, they are 0 at the top, and then down at the bottom is the 50 mil mark. So this would be like 49, 48. So that's what is now, if we invert it, that's what is at the top of our burette. And if we're using this burette to measure the volume of a gas, there's a big area at this tip, this area here, that's uncalibrated. There are no marks down below the 50 mil mark. And so that is up in this area right here. That's where our gas is. So we need to take that uncalibrated region into consideration. And we need to do that when we're trying to measure the volume. All right, so I'm going to use our inverted burette here and kind of show what the areas are. So from here to here is the volume of our gas. And from here, from the 50 mil mark to the 0 mil mark, that is 50 milliliters. In your procedure, it's going to ask you to find this uncalibrated portion. It's also going to ask you to record the final burette reading. Which would be right there. So how we can put all these numbers together to find the volume of our gas is we can take the uncalibrated portion and the 50 milliliters and subtract out this final burette reading. So we're taking this entire area and we're subtracting out this area, and that will get us the volume of our gas. So the volume of the gas is equal to 50 milliliters plus the uncalibrated portion minus the final burette reading. So now we have the information we need to find the pressure of the gas. Now we can find the volume of the gas. The last one is to find the temperature. This one's the easiest one. We're just going to use a thermometer and we're going to take the room temperature reading. And once we have these variables, which we'll have if you follow along with the results section, we're using those to find the moles of hydrogen gas. We would take PV equals nRT, and we're going to rearrange it so that moles is on one side. Now, we just have to insert these. So we will have the pressure of our hydrogen gas, we'll have the volume of our hydrogen gas, we'll have the temperature of our hydrogen gas. R is always a constant, and we can find the moles of H2. And we can use that moles of H2. So if we have moles of H2, we can use that to find moles of our metal. In this example here, if I started off with my calculated moles of H2, I can see that there are 3 moles of hydrogen for every 1 mole of aluminum. And so the moles of hydrogen would cancel out. I'd put in my number right there, and I would be able to calculate moles of aluminum. So we just talked a lot about how we would collect volume, temperature, and pressure data about H2, and we would use that information to find the moles of hydrogen, and then we could use that information to find the moles of the metal, as long as you know what mole-to-mole ratio your metal is. So we have to know what the metal is to be able to calculate the moles of metal. And once we have moles of metal, we can use our mass of our piece of metal before the reaction to find the grams, and once we take the grams and divide them by the moles, we will get the molar mass of our metal.